Here in session 46, we're going to be addressing how to graph simultaneous equations. Over the past few sessions and lessons, we've been taking a look at how to determine answers or solutions to simultaneous equations. Now we're going to take a look at actually graphing the equations themselves. First of all, you need to remember, in order to graph a line for a particular equation, you need to find out two different points that exist on that line. Once you find those 2 points, all you have to simply do is connect those 2 points and extend that line segment past those points indefinitely, and that becomes the line that is then the graph for that particular equation. Here is a pair of simultaneous equations. 2x plus 3y equals 6, and 3x minus y equals 3. We could go ahead and try to solve this by addition or subtraction or what have you and come up with the exact x and y value. But what we're interested in here is more than just finding out the exact point at which the coordinates for that point are a solution to both of these equations. We actually want to graph both equations themselves. So then, how can we find out 2 points that exist on the line of the graph of equation number 1 here? You simply can just start selecting some points. For example, for this first equation here, what if we make x 0? What would y be? Well, we put in a 0 for x. 2 times 0 is 0. So that then just leaves us with a 3y, a positive 3y here on the left. 3y equals 6. 3 times which number equals 6? Well, 3 times 2 equals 6. So we know that one of the points on this line is x comma 2. Let's choose another point and find out what the values are for x and y. What if we make y 0? We'll go ahead and stick 0 then in the y portion of our coordinate pair here. Well, when y is 0, 3 times 0 is 0. That then just leaves us with 2x on the left. 2x equals 6. Well, 2 times which number is 6? Well, 2 times 3 is 6. So at this point, we have two different ordered pairs here that represent solutions and points for this particular equation up here. So let's go ahead and graph those 2 points. The first one is 0, 2. So we come here to our origin, which is x at 0, and come up 2. Okay, there's our first point. Our second point is 3, 0. So I'm going to come over here, start at the origin, come over 3, up 0, which means I stay right there. And that now represents the second point that's on that graph. So then I can now just connect these lines, or excuse me, connect these points with a line that then becomes the graph of that particular line. And remember, a line goes on forever, so it would continue to extend this way and down this way indefinitely. That takes care of the first equation. Well, let's take a look at the second equation. Let's try to find two ordered pairs for that one as well. First of all, let's go ahead and make x equal to 0. Well, if x equals 0, what's y? Well, x is 0, 3 times 0 is 0. That leaves us with just minus y on the left and then positive 3 on the right. Minus y equals 3, so what's y equal? Well, y equals a minus 3, because remember, a minus of a minus is a positive. So when x is 0, y is minus 3. That's a point that's a solution to this second equation. Let's choose another one. What if we go ahead once again and make this times 0 for y? What's x? Well, let's put in a 0 up here for y. We now have 3x minus 0. That's just the same thing as 3x. So we have 3x equals 3. 3 times what number equals 3? 3 times 1 equals 3. At this point, we now have two different points that are solutions to this equation. And remember, all you need to have to graph a line is 2 points. So let's come here and find out the graph for these. Plot these points. 0, comma, minus 3. Here's our origin where x is 0. And then down minus 3. Our next point is x is 1, y is 0. Well, that would be right here. We now have our 2 points, and we can connect those with a line. So we can see here that we now have 2 points, or excuse me, 2 lines that crisscross and intersect each other. Now, without trying to determine the exact answer right now, the point, the place at which these two equations, the graphs for these two equations intersect, represents the point. The x-coordinate and the y-coordinate for that point represent the answers to the solving of these two simultaneous equations. For example, if we had tried to add these equations together, multiply this by 3 to get a minus 3y, and then we combine it, add the 2 here, whatever result we would get from that, whatever the x value is and the y value is, would represent that point right there on the graph where the two intersect. So once again, on the graph for simultaneous equations where they intersect each other, that represents the one common point, one common solution that both of those equations have with each other. Over here on the next screen, we're going to take a look at two more equations here, but they're in a slope-intercept form. If you remember from several sessions ago, we looked at the slope-intercept form of an equation, and that is where you have y all by itself on the left-hand side, and that equals some value, some constant, times x plus some other value, some other constant. The reason why we go ahead and write both of these equations this way here is that we can also graph these equations without having to solve the simultaneous equations. But this is a slightly different approach. The slope-intercept form gives us some additional information that we did not have on the previous screen when we were trying to solve those two equations. If you remember, when you have the slope-intercept form of an equation, the value that's being multiplied by the x represents your slope. And then the constant that you have over here at the right that's being added or subtracted, that's being added here, represents your y-intercept. So let's go ahead and plot some points. We know that our y-intercept for this first equation is 4. Because if we were to stick a 0 in for x, 1/3 times 0 is 0. 0 plus 4 is 4. When x is 0, y equals 4. So we come here to 0. That's our origin, and up 4. So there's a point that represents our y-intercept. Now, we could choose to find our other point by just choosing a value of x and plugging it in here and calculating what y is. But we also could calculate what the next point would be simply by looking at the slope. Remember, the slope equals the rise over the run. The rise representing our change in the y direction, and the run representing a change in our x direction. Rise over run. So for every rise of 1 in our slope of 1/3, we have a run of 3, and these are both positive. So we come to our y-intercept here of 4, and we go and we do a rise of 1, which would be up 1, and a run of 3, which would be 3 to the right. There are our 2 points. Now we can simply connect them together, and there's our line that represents the graph of this equation. Let's take a look at our second equation. Same thing. We have a slope-intercept form, so this minus 6 here tells us the y-intercept, because once again, if we make x 0 here, 2 times 0 is 0, 0 minus 6 is minus 6, that tells us our y-intercept. So we go x to 0 and y to minus 6. The next thing that's going on here is we have our slope given to us. Our slope here represents 2. And remember, a slope is rise over run. Even though we don't see a fraction here, the number 2 could be rewritten as 2 over 1. 2 over 1 is the same value as 2. So if it helps you to see it that way, you can slide that 1 underneath the 2 with a division symbol, a fraction bar. And this will help you determine your rise over your run. For every 2 on your rise, you run 1. So remember, your rise is on the x-axis. We start at this point down here and we go up 2, which represents the 2 on the rise, and over 1, which represents the run. Then we take and we can connect those 2 points together, and if we extend it as such, we'll see that they intersect over here at this point. So then you have a couple of different methods for graphing equations. You can just choose points at random, and once you get 2 points for a particular equation, you can go ahead and plot those 2 and connect them. Another method is that if you have equations in the slope-intercept form, which is what we do here, you can go straight over to your constant at the far right and plot that point, because that's going to be your y-intercept, 0, 4 in the first equation, 0, minus 6 in the second equation. Once you get that point, you come to the value, the constant that's being multiplied by your x variable, and that represents your slope, your rise over the run. You then take that rise over the run, go to your intercept, and do what the rise over the run tells you to do. That'll give you your second point, and then you connect them, and that becomes the graph then for your particular equations that are in the slope-intercept form. And once again, where they intersect here, even though we do not have the exact x and y coordinates for this point here, where they intersect would represent the one common solution that both equations have in common with each other. So lastly, when you're graphing simultaneous equations, the coordinates of the point at which the 2 equations intersect represent the common solution to both equations. Okay then, that finishes up session 46.